All right, so we are going to do some nuclear equations today. So first thing we're going to do is write out a nuclear equation for the alpha decay of Pa231. So we are going to write Pa and then 231. That is the mass number that goes on the top left of the isotope notation. Next, we need to find the atomic number. Now, the atomic number is going to be in the periodic table. So we find Pa, it's right there. Atomic number is 91. Okay, so we go back here, we write 91 in the bottom left. Okay, so that's where the atomic number goes. Then, since this is a decay, we are going to do an arrow, and we're going to figure out our products. Now, since this is alpha decay, one of the products for alpha decay is always going to be 4, 2 helium. So mass number of 4, atomic number of 2, helium. That will always be one of the products of alpha decay. Okay. The other one is going to be what's left of the Pa when the alpha particle splits off of it. Okay. So the way we figure that out is in order to make the helium, we have to have 2 protons and 2 neutrons leave the Pa. So what that's going to do is decrease the atomic number by 2 and decrease the mass number by 4, which is where we get these numbers from. Okay, so 231 minus 4 is 227. 91 minus 2 is 89. Okay, then we have to identify what that new element is. Okay, since the atomic number changed, we have to check that. So atomic number 89 is AC, actinium. So we just go back here, we put AC, and that's it. That is the alpha decay of Pa. Next, we're going to do a beta decay of Fr, which is francium. So we do the same, or it's the same idea. We start with 223, Fr. We find Fr on the periodic table. It is francium 87. So we put 87 here. Okay. Oh, not a plus. Sorry. Don't know why I did a plus. We do our arrow because that's going to decay into 2 things. Now, for beta decay, the particle for beta decay is 0, -1, E. Okay. And then we are going to do our product. So what this is doing is it is taking, it is adding an atomic number, I'm sorry, a proton to this. Okay. It's taking one of the neutrons from francium and turning it into a proton. So it is going to increase the atomic number by 1. So 223, because no mass changed. Okay, we took a neutron, we turned it into a proton. It's still inside, so the mass didn't change because neutron has a mass of 1, proton has a mass of 1. So mass doesn't change. The atomic number is going to increase by 1. Okay, so how we get that is we take 87 minus -1, and we get 88. Okay. Now we have to again check what element that is. That is radium Ra. So we put Ra right there. And that's it. Okay. All right, we're going to do a couple more. Next one is SM149. So 149 SM. We check and see what that atomic number is. SM is 62. So 62 goes on the bottom. We do our arrow. Since this is alpha decay, that's going to be a 4, 2 helium. That is an alpha particle. And then we add what's left of samarium. Okay, so 149 minus 4 is 149. 45. 62 minus 2 is 60. We check and see what element that is. That's Nd, neodymium. And there we go. That's it for the alpha decay. Next one is beta decay of PM. So 165 PM. PM is promethium, 61. We do our arrow. This is beta decay, so that's 0, -1, E. And what's left? 165 minus 0 is 165. 61 minus -1 is 62. And that is, oh, samarium, SM. Look at that. And there it is. That is how you do the two different types of nuclear equations. Now, there is the third type, gamma, but that is only energy. There is no particle released when you have gamma decay, at least when you have just gamma decay. Gamma decay usually is coincided with either alpha or beta, but specifically gamma decay doesn't affect the structure of the atom it is affecting. Okay, that's it for that.